try to push on the opposite direction, kx. Same thing, the damping will push on the opposite direction, bx dash. So the forces we have only two forces, kx and bx dash, because if you remember, we said mg will cancel with the static deflection. So we will not account the weight for the mass m. It will cancel with the static deflection, and the motion is up and down like this. The motion will be up and down about the equilibrium position. And then if we write Newton's second law for a system in translation, we will write it this way: sigma force is equal mass times acceleration. We write, or we investigate all the forces acting on the system. We will find we have the two forces minus bx dash minus kx is equal to mx double dot. If we rearrange this equation, we can write it in standard form: mass times acceleration plus damping times velocity plus stiffness times displacement. This will be equal to 0. And it is a second order ordinary differential equation with constant coefficient m, b, k are constant. And it is 0. It's homogeneous because the motion is only due to the initial conditions. So it's a homogeneous because the right-hand side is 0. And that's why we call it free vibration. Because of the 0 here, we call it free vibration. Free vibration. So now it is the second order, as you can see. If we substitute the mass and then the damping and then the stiffness, we end up by having this equation here. And if we assume that we have initial conditions x0 is equal to x0 and initial velocity was 0, and then this is, you already covered it in chapter 2. It turns out to be solving a differential equation in S domain in using Laplace transform, and you know the solution. So if we take Laplace transform of both sides, this is what we got here now. Laplace transform of the second derivative plus 4 times Laplace transform of the first derivative plus 40 x of s is equal to 0. Now, if we substitute the initial conditions, x0 here is equal to x0, and x dot 0, this one is 0, and we solve for x of s, we will find x of s is equal to this amount. S plus 4 over s squared plus 4s plus 40 times x0, which is the initial condition. So it means that the motion will be caused by this small x0, by this initial condition. We can write it also in the form of the output over the input. The output is x of s, we are looking for it. The input will be x0. We can find it to be s plus 4 over s squared plus 4s plus 40. In system dynamics and control, we can represent it also by this diagram or by this block, where in the right-hand side we put the output, in the left-hand side we put the input, and we say if we multiply the input by the transfer function, we got the input. So this handwriting is equal to this x of s, the output, will be equal to x0, the input, times g of s, which is the transfer function. So the transfer function is a relationship between the output and the input when in Laplace transform. So if we look now for the denominator, the roots of the characteristic equation, we can write the term s squared plus 4s plus 40. We can write it 40. We can write it as 36 plus 4. This is 40. And then we can decompose this one into a complete square, s plus 2 squared plus 6 squared. And if we solve this equation, you will find two poles, s1, 2. The real part will be minus 2. This is the real part, minus 2. And then plus or minus j6, which is the imaginary part, which is this one. So the complex are pure, are complex conjugate, the real part and imaginary part. So we can write x of s in this form, s plus 4 over s squared plus 4s plus 40. 4, I can split it into 2 plus 2. And I will take this one alone, s plus 2 times x0. This one is here, s plus 2 times x0. And then 2 over x. Every term I will write it alone. So I will have x0 in common. x0 here and x0 in common. The first term is s plus 2 over s plus 2 squared plus 6 squared. This is, you know, this is simply a cosine term that is shifted by 2. And this is a sine term that is shifted by 2. So I need to have 6. So I need to multiply by 6 and divide by 6. This is what I have done. So when you multiply by 6 and divide by 6, this is 2. It will go with 6. You will have 1 over 3. So at the end of the day, you will have x0 exponential minus 2t cosine 6t plus 1 over 3 exponential minus 2t sine 6t. If you take x0 exponential minus t common, so if we take it x0 exponential minus t or minus 2t common, you will have cosine 6t plus 1 over 3 sine 60. So the solution will be a decaying term, which is exponential minus t, and that is minus 2 is the real part of the pole, the real part here. Cosine 60 and sine 60 are the sinusoidal terms, and they are provided from the imaginary part of the pole. So this, we can combine them into just one term, either sine or cosine term. When we put sine term here, we put plus 71.56. I will show you in details how to get from here and here. So this is a decaying exponential function that written, or that is the slope can be shown to be like this. The decaying envelope is exponential minus 2t, which is this one. This is due to the this is due to the real part, and a sinusoidal one, or sine or cosine, inside this envelope, inside it, which is due to the imaginary part. So the imaginary part is responsible for the sinusoid, and the real part is responsible for the decay. This is when we have, Shabab, the equation. We have a damping into the equation. See the damping, what it does, it put an exponential term that is decaying. So the solution will be decaying after some times. The solution or the motion will die. And since here we have a damping, we have, in addition to omega n will be always, omega n is always stiffness over mass, which is K over M. This will not change. And you have another frequency, which is called the damped frequency, omega D. And the time from here to here, is called the damped period. So because here we have damping motion, the natural frequency will stay always as it is, stiffness over inertia, always. Even if we have damping, the natural frequency will stay exactly the same because it's a property of this system. But in addition, we will have a damped frequency called omega D. So this is when we have a damping. And if there is a MATLAB, since we are dealing with MATLAB also, there is a comment called PZ map. PZ map means you draw the pole and zero. PZ stands for PZ map, pole, zero, map. You can map them. You can see the numerator and denominator in your MATLAB. This is the equation, the characteristic equation. And this is the P0. This is the S is equal to 0. And the S is equal to -4 is here. This is -4 from here. Usually MATLAB designates 0 with 0 and the pole with X. The pole are here. The real part is -2, as you can see. And the imaginary part is somewhere here. You look between -5 and -10. You will see that -j square root of 6, -j6. And this is also plus j6. It's somewhere here between 5 and 6. And the response will look something like this one. It's decaying. After 2 seconds, the response will decay and it goes to 0. So this is when we have a damping. We use also, Shabab, the work and energy. The work in a mechanical system is simply a force multiplied by distance, and it is what, Shabab? It is a scalar product, and it comes from the F dot D. F dot D is a scalar product. So the work, if you displace it from one position, for example, the solid line here, to the dotted line, the final position. So F will be F times D. Cosine 0 because there is angle 0 here. So it will give you F times D multiplied by 1. But if it is acted by an angle theta, it will be W equal to FD cosine theta. And as you can see, this one is, since we have a dot product here, this term will be a scalar product. The unit of the work is simply Newton times meter or joule. Usually it's expressed like this, J, force times distance. If we have a spring, Shabab, the spring, since the force on the spring will be Kx, so the force on the spring will be Kx linear force, as you can see here. It's a linear relationship. And then W will be the integral from 0 to x kx times dx. If you integrate this one, you will find that this one is only the area of the triangle. If the area the triangle, half k times x squared. Similarly, for a torsional spring, the work done will be half kt theta squared. And this is the work for the spring. The work for the gravitational energy, you know, it's simply mg times h. Mg is the force times the distance is h. The energy is defined as the energy ability to do work, and it can be found in many different forms and can be converted from one type of energy to another type of energy, from electrical energy to mechanical energy, from chemical energy into electrical energy, and so this is an electric motor converts electrical energy into mechanical energy. In the battery, you can see that the chemical energy is transferred into electrical energy and so forth. The conservation of energy, Shabab, the conservation of energy says that the energy can neither be created nor stored, destroyed, but it is simply transferred from one type to another type. So this means that the increase in total energy within a system is equal to the net energy input to the system. If there is no energy input, there is no change in total energy, and we can say that the system is conserved. Potential energy, it's due to the position here. M is displaced with an amount will fall down with an amount H. So the potential energy will be simply mg times H. It doesn't matter wherever, no, it's conservative force. So it doesn't matter whether it falls like this or like this. It does not depend on the path. The path is not important, you know. So that's why we call it conservative forces. Mg is conservative force. So the amount is H is always the same H. So the mechanical energy, only mass and spring can store potential energy. The change in the potential energy stored in a system is always equal to the work required to do the change in the system configuration. So potential energy, when we talk about potential energy, we have to specify a datum, which is extremely important, or reference. So because here, this mass will have potential energy equal mgh with respect to the datum here. But if we take the datum, this is our reference here. If we take this m will be mgh from here to. But if we take the datum to be here, now the potential energy will be 0. So the spring here, the spring will always have the potential energy F dx, which is equal to half kx squared, elastic deformation. So F times dx will be kx is the force, integral dx will give us half kx squared. If the spring is attached between two positions, x1 and x2, so it will be the final position or the final kinetic potential energy minus the initial potential energy, half kx2 squared minus half kx1 squared. Similarly, for the potential energy for a torsional spring, this is what we have, half kt theta 2 squared minus half kt theta 1 squared. Kinetic energy is due to the motion. Because there is a motion, the kinetic energy is always half mx dot square. Maybe you have noticed, Shabab, that I am going a little bit fast. All these topics, you know them, and it is just a revision. So the change in energy between two positions, it will be half mx dot square. At position 2, the velocity was x2 dot square, and at position 1, the velocity was on x1 dot square. So this is the kinetic energy, the change in kinetic energy for a system in translation. For a system in rotation, we will have the kinetic energy half j theta dot square. Delta t is equal to half j theta dot 2 square minus half j theta dot 1 square. You can see the analogy or the comparison between the two type of motion. This is the translation is m, rotation is j. The translation is x dot or v. The translation here, the rotation is theta dot or omega. Usually this is known as omega and this is known as v. And you were using it in dynamics, half mv square. And this one half I omega square, or half j omega square. So these are the type of energies. Dissipation energy, Shabab, it's always called because it's due to damping and the loss in energy. It's given by this amount, delta W F dx. F is B x dot, which is the force, times dx. Dx, we can write it, x dot, we can write it dx over dt times dt. Or you can just integrate x dot with respect to dt. Then dx over dt is nothing but it is x dot. So this is x dot multiplied by x dot will give you b x dot square. And this is the work done by the damper, so which is dissipated in terms of heat. The power is usually defined as the rate of change of the work with respect to time. So dW denotes the work done during an interval time dt. And it is Newton meter per second, which is usually joule per second or watt. This is the work done by unit time. We usually call it work done by unit time. It's called the power. When we are dealing with this type of element in mechanical system, the mass, spring, and damper, they do not produce energy. They store energy or dissipate energy. So we call them passive elements. But energy producing, those elements who produce energy, these are such external forces and torques and actuator, and so we are not dealing with them in this course. We are dealing only with passive elements, which are mass, spring, and then dampers. So these are called passive elements. For conservative system, Shabab, we have the energy is always constant. Change in total energy will be the net work done on the system by external forces. Since there is no external forces to the system, when there is no external forces to the system, so the work done here will be equal to 0. And the energy, the change in energy will be equal to 0. The change in energy will be equal to 0, to the energy itself is constant. The kinetic energy plus the potential energy at any time is equal to constant. So the rate of change d over dt of t plus u equal to 0, and this is called the conservation of energy. Conservation of energy says that the rate of change is equal to 0 and t plus u is always constant. So a system is said to be conservative if no energy is lost due to the friction or energy dissipation. If no work done on conservative system by external force, so the total energy of the system remains constant. And we have this equation. T plus u is equal to constant, and d over dt, t plus u is equal to 0. This is from here, from this position. So, Shabab, this is what we have for the conservation of energy. If we take the spring and the mass, if you remember, we have seen this example when using Newton's second law. If this is x, the motion is down, we can write the kinetic energy of the spring to be half mx dot square. This is the kinetic energy of the spring. This is the potential energy of the spring, also mass spring system. Sorry, this is the kinetic energy of the mass. This is the mass for the mass, because the mass has kinetic energy and the spring has potential energy or strain energy. This is for the spring. And we have T plus U is equal to half mx dot square plus half kx square. This is the total energy. Now, if we differentiate this with respect to time, we will find when we differentiate half mx dot square, it will give me 2 times half m x dot. When you square it, it will be x double dot, and then x dot. This is when you differentiate the first term. Plus, when you differentiate the second term, it will be 2 times half times k times x dot. So this is what we got here now. We take x dot out, we simplify the 2 with 2, and since we will obtain this equation, or at the end of the day, we'll obtain this equation, x double dash plus k over mx is equal to 0, which is equal the same equation we have obtained before when we dealt with Newton's second law. When we have dealt with Newton's second law, we got the same equation, if you remember. And this term, k over m, is usually known as the natural frequency of the system. So we can write this equation x double dash plus omega square nx is equal to 0, where omega square n here is equal to simply k over m. And this is the free vibration motion of a mass damper system using the kinetic energy and potential energy. And this amount is always constant. So here we go to the potential energy is equal to the kinetic energy. What does this mean? T max is equal to U max. It means that this spring is moving between 2 positions. We have 2 positions here. If this is the equilibrium position, and then the mass can come here and can go here up to here. So when it vibrates, it will go between the upper max and then like this. It will be vibrating between the 2 upper limits. So if we take this as the equilibrium position, the kinetic energy here, the kinetic energy T is equal to 0, but V is equal to V max. While at this position, the potential energy V is equal to 0, but T is equal to T max, and so on. At any point is such that if we add this T plus V equal to T plus V should be equal to V plus T here. So T at this position, T1 plus V1, وهنا V2 T2. So T1 plus T1 plus V1 is equal to T2 plus V2, give you V max is equal to T max. So this is T max is equal to V max. Now we assume just classical solution like we do. If we assume that a solution to the equation is simply x is equal to half A sine omega t, where A is the amplitude, and sine omega t, omega is the frequency, and phi is the shift. Just take this quantity Ax, or x is equal A sine omega t plus phi. The kinetic energy is defined as half mx dot square. Here, shabab, we are just replacing m by k omega. You remember from the previous slide, I told you omega square will be equal to k over m. I'm replacing the m by k. Here you can say that m is equal to k over omega square. I'm replacing the m by k over omega squared. So I can write it half k over omega squared, this is m, times x dot. X dot, when you differentiate this one, you will have x dot is equal to a omega cosine square omega t when you differentiate it. So here, this is x dot square. When you differentiate this one, we square it here. And then this turns out to be half k, because omega will cancel with omega, a square cosine square omega t. The strain energy, which is given by U, is equal to half kx squared. X squared, we square here everything. If you square here, half k a square sine square omega t, you square it. And then if you add t plus u, if you add them, you will have this term plus this term. You take half ka common, half ka square common here and here, and you have cosine square omega plus phi sine omega square t plus phi. This term is equal to 1, always equal to 1. So the total energy of the system will be half ka square. Yani it will be depending on the stiffness and the amplitude of vibration. And this is the total energy of the spring, which is this one here. A plus E is equal to T plus U is equal to half K A square. And whatever, all the time, you square the kinetic energy. This is the kinetic energy, and this is potential energy. Wherever you add this point to this point, this point to this point, this point to this, you end up by having a constant energy, which is this one, which is equal to half Ka square, here and here. واضح شباب؟ It's always the constant. It's always equal to a constant. The kinetic energy for a rolling motion, we have the disk, which is shown in the figure, rolls without sleeping. Find the equivalent mass or inertia, equivalent mass of inertia. Since the system here, or the disk, is translating and rotating at the same time, so the kinetic energy for translation will be equal to half mx dot square, and the rotation will be half j theta dot square. For a non-sleeping condition, since there is no sleeping, we can write x is equal to r theta. So x dot will be equal to r theta dot. This is, you know it from dynamics. So if we write the equivalent translational motion, we can write the half mx dot squared. This is x because x is translation. And they can substitute theta here, theta or theta dot. I can substitute it by x dot over r. This is what I'm doing here, x dot over r, or x dot square over r square for theta dot square. So if you look here, you have half common and x dot common, x dot square common. You take it out, and you have this expression half m plus j over r square x dot square. If you compare it to the standard equation for kinetic energy, you will say, oh, this is the equivalent mass. The equivalent mass for translation, half m x dot square. So the equivalent mass will be this term. Now, if you want to write this energy, the kinetic energy, in terms of theta, you will just substitute x dot by r theta dot, and you will have theta dot in common. So this will be half j equivalent theta dot square. And j equivalent in this case, it will be mr square plus j, because it's in standard form, half j equivalent theta dot square. We use the energy method to find the equivalent mass and the equivalent stiffness. We have a small problem here. They are asking us to use the energy method to calculate the equation of motion and natural frequency of airplane steering mechanism for the nose wheel of its landing gear. The mechanism is modeled as the single degree of freedom system illustrated in the figure below. The steering wheel and the tire assembly are modeled as being fixed at the ground for this calculation. So the steering rod gear system is modeled as a linear spring and mass system MK2, oscillating in the x direction. The gear shaft mechanism is modeled as the disk of inertia J and torsional stiffness K1. The gear J turns through the angle theta such that the disk does not slip on the mass, obtain an equation in the linear motion of x. So the whole story, we have a translational system, which is this one, which is composed of K and M. This is in translation. It moves. The motion will be in this direction like this. And we have a rotational system that is rotating like this. So we have a shaft with a stiffness K1, and we have a disk with inertia J. So this will be rotating, and this will be this will be translating like this, and this will be rotating like this one. So since we have two masses or two inertia, the kinetic energy will be equal to the kinetic energy of translation plus kinetic energy of rotation. Translation because of this mass, and rotation because of this disk. So the translation for the kinetic energy will be half mx dot square plus half j theta dot square for rotation. These are, we finished. There is no kinetic energy. Class, we finished. The potential energy, there will be a potential energy of the spring K2 that is due to translation, half K2x squared, plus the potential energy of the spring or for the shaft K1, which is half K1 theta to theta squared. So these are the kinetic energy and the potential energy or the strain energy. We add them, we add these two energy together. So the total kinetic energy will be this plus this. So this one will be T, total energy, plus this one. If we add them and then take the differentiation d with respect to dt of the T total energy plus V, we should equate it to 0. When we equate it to 0, we'll differentiate and then we got the energy. So this is the total energy. This is the kinetic energy here, T. And this one will be the potential energy, U. And then since there is shabab, no sleeping or the non-sleep condition, it requires that theta is equal to x over r, and theta dot will be x dot over r. Now we are going to find the equation of motion in terms of x, لأنه هو قالنا find the equation of motion in terms of x. So we can rearrange this one. Half m, I can substitute theta dot by x over r. So I will write the x dot over r square, and I will write the kinetic energy half m j over r square m equivalent. This is the equivalent mass. I can write also here, from here, I can write x square, which is this one. Theta can be replaced by x over r, and I will have half k equivalent, equivalent, which is K2 plus K1 over R squared. So this is the K equivalent, and this is the mass equivalent. So I can write my equation to be simply half M equivalent, half mass equivalent X dot squared plus half K equivalent X squared. And now if I differentiate this one, if I differentiate this, when I differentiate this equation, I will have half will go with 2. When you differentiate this one, 2 will go with half, like this, half, and then we have 2 m equivalent x dot x double dot plus 2 times half K will go. So at the end of the day, I will get this equation. I will obtain this M equivalent x dot x double dot plus K equivalent x dot equal to 0. Or if I simplify by x dot, since x dot is not 0, I can simplify it. So my equation turns out to be M equivalent x double dot plus K equivalent x is equal to 0. Or simply x double dot plus omega square n x is equal to 0, where omega n here is equal to K equivalent over M equivalent, where K equivalent, I can substitute it by K2 plus K1 over R square over M plus J over R square. Any question? Any question, Shabab?
دكتور
تفضل.
في equivalent stiffness should be K equivalent or J equivalent?
لا, stiffness is K. stiffness.
So there is a mistake here. طيب.
لا هنا stiffness. sorry, هذه قصدك هذه K equivalent.
ايوه
K equivalent. This is K equivalent. شكرا انك نبهتني على الخطأ. This is K equivalent شباب. هنا لو قلنا, if he asked us to find the equation of motion in terms of theta, هذه راح تكون J equivalent. In terms of theta راح هذه تكون J equivalent. بس هذه it will stay always K equivalent. We have another system which is similar. A control pedal of an aircraft can be modeled as the single degree of freedom system as shown in the figure below. Consider the lever as a massless. هذا الليفر هنا, this lever from here to here, L1 L2 is massless, يعني ما عنده mass shaft, and the pedal as lamped mass at the end of the shaft. Use the energy method to determine the equation of motion in terms of theta and calculate the natural frequency of the system. Assume the spring to be unstretched as theta is equal to 0. There are two positions, Shabab. Position 1, which is in blue one here, I will leave it in blue like this. When the system was here, the pen is not properly, I don't know what's happened with my pen. Today it's very thick and they cannot adjust it. You know, your instructors with the technology are a little bit late behind you. You are much advanced. So this is the original position, it was here. And this is the original position, it was here. And then when we shift a little bit this mass like this, for this position with an angle theta, we have the spring is deformed by an amount x here. Amount from this position to this position, small amount, which is x. And here also another amount, which is x, another x. So this one will be x2, I will call it x2, and this one I will call it x1. Is it clear, Shabab? Like this. This is the original position, and then this moving like this, here, x1, and this one is moving from here to here, x2. So this is it from here. The arc here, this one is x1, and the arc here is x2. Is it clear? So what we have here, we have a mass, only mass, which is this one, mass. And the mass is having kinetic energy. Kinetic energy will be half m. I will call this the arc here, this arc here x2. This x2 is equal to L2 times theta, because we have small motion. X2 is equal to L2 times theta, and this is what we are writing. T is equal half mx dot square, or half m L2 square theta dot square. Do you agree with that, Shabab? X1 here, X2 here, X1 here, this small deformation here, بالنسبة للspring, I'm writing half K x1 square. This is x1. So x1 will be L1 times the same angle theta. This is theta. The same angle theta. It's the same. واضح شباب? Is this clear? Is it clear شباب? Shabab, is it clear?
Yes, clear, Doctor.
Okay. So let's continue. X1, remember X1, I will write X1 will be equal to L1 theta. X2 will be L2 theta. This is X2 here, and this is X1 here. Now, we finished with the kinetic energy. We wrote the potential energy of the spring, but there is the potential energy of the mass that is moving from here to here. Potential energy of the mass, we are going to write it this way. Suppose we have, I will take this position here as a pendulum. I will take the position here as a pendulum here. This is the original position, and the pendulum is moving up to here. So it was moving this way. Now this length is from here to here is L. And this is the angle theta. And this L is the L here. But what is this length, Shabab, min hina ila hina? This length from here to here. From this point to this point. Can anybody tell me what will be the length from here to here?
L cosine theta.
So this term from here to here is, the blue one is L2 cosine theta. And this length, the original length is L2. And this is also L2. So now what I need only this term, here, H. This H will be equal to L2 minus L2 cosine theta. That's why we are writing here. The potential energy will be mg times H. H is equal to L2 minus L2 cosine theta. Is this clear, Shabab? Is it clear? I will repeat. So the original length is here. Just follow me slowly. So the spring has a length L, L2, or the arm is L2. The mass is here. The mass is moved a distance like this from here. So this is still L2, صح? But the H, and I need the H, which is this one. This is H, the difference in height. This difference in H, Shabab, will be equal to the total length L2, minus this length, which is from here to here. Minus this length, I will repeat the color here. Minus total, this is L2, as you can see, minus this length from here to here. This is theta. If this is L2 and this is theta, so this length, the red one, will be L2 cosine. And that's why we are writing H will be equal to L2 minus L2 cosine theta. And this will be the potential energy due to the gravity or due to the mass. So that's why we are writing the potential energy is one potential energy due to the spring and the other potential energy due to the gravity. Once we write these two equations like this, I add them, T plus U, I will get half M L square theta dot square, kinetic energy, plus half K potential energy due to the spring, potential energy due to the mass. So if I take differentiation with respect to this, I will have ML2 square theta dot double dot plus K L1 square theta dot plus MGL2. This one will be 0, and minus cosine theta will give you sine theta. Now, Shabab, this one is a nonlinear equation. If you arrange this, it's a nonlinear equation because of the term sine theta. But now what we will do, we will assume small motion. For small motion, sine theta will be equal to theta. For small motion in radians, should be in radians. So if we assume small motion in radian, the equation, this is the assumption, and the equation can be written like this: ml square theta double dot plus k l square 1 mgl2 theta is equal to 0, and can be written also in standard form. You can take this one as I equivalent, inertia equivalent times theta double dot, plus k equivalent times theta is equal to 0, where I equivalent is this, and k equivalent is this one, and the natural frequency of the system will be equal to K equivalent over I equivalent, which is equal to omega n, which is this one. Remember, Shabab, the natural frequency is always equal to stiffness over inertia. Stiffness, yani K over inertia, over mass. Any questions, Shabab? This is the equation of motion. And finally, we found the equation of motion using the energy method. I don't know if we have time for this problem, but if there is no time, it's the same. We solved it together. Figure 1 shows a homogeneous cylinder R, and the mass M is free to rotate about its axis. It rotates about the axis here. And that is connected and roll through a spring, but they're rolling without friction. There is no friction, and there is no slipping also. Assuming the cylinder rolls on a rough surface without sliding, obtain the kinetic energy and potential energy of the system, derive the equation of motion for the total energy that is constant. Same thing. We have seen this. This is due to the kinetic energy half mx dot square. This is translation. This is rotation. And at the end of the day, we can write T is equal half mx dot square plus half j x dot over r square, which is equal to this one. Now, we add the two energies. We add the two energies. U is equal to half kx squared because of the potential energy here. So we end up by having this equation. So we know that J is equal to half mr squared. We substitute J by half mr squared. We can write the kinetic energy to be half mx dot square. Maybe somebody will ask me, how did we get this? Hina Shabab. If we add simply J half mr square, if we add m r square plus half mr square, we will obtain 3 over 4 mr square. So 3 over 4 mr square, this is what we got here. 3 over 4 mx dot square plus half k square is equal to constant. Or if you differentiate with respect to time, you will get 3 over 2m x dot x double dot plus k x dot is equal to 0. Or you simplify it in standard form. You write it x double dot, always make the coefficient of the second derivative equal to unity, so that you will obtain here omega n square. So this one will be omega n square. Try to write it always, Shabab, the coefficient of x double dot 1, so that you will get here omega n square. And omega n in this case will be equal to 2k over m, which is the natural frequency of the system. شكرا على حسن الانتباه. Let me just take the attendance. Please, if you have any question, let me know. منير موجود معنا اليوم شباب؟ منير العوة. منير أهلا منير. أهلين. كيف حالك شيخ منير؟ غالبي فيصل. دي غالبي فيصلو يا فيصل، ما هو موجود اليوم، راحت عليه نومه شكله. المسعودي عبد العزيز. أهلين عبد العزيز. الملا ماجد. يا شباب لسه والله ما الكتاب. we don't know. أنا I'm putting the notes. So far you can use my notes. And I posted the homeworks. And I will post also, inshallah, I will do my best to post the solved problems, inshallah, before the exam. هذا وعد مني. I will post, I mean, some problems are solved in the textbook. I will post them inshallah بإذن الله. For sure. هذا وعد يعني. Don't worry. ننتظر. لسه ما جانا أي شيء من الإدارة. الملا ماجد. ألين ماجد. ألين حسين. في واحد فاتح المايك والصوت يجي. أحطاني حسين.
موجود يا دكتور.
أهلين. مين فتح المايك يا شباب؟ المحمدي عبد العزيز. اهلين عبد العزيز محمدي.